So I'm David Dempsey. I'm the National Treasurer, but I have the distinction among the officers that I have actually met Joe Gallian. I'll tell you more about that. We're delighted to have Joe with us today. He's a graduate of Slippery Rock University. Shout out to Pennsylvania Pi chapter there. Went on to University of Kansas and Notre Dame. And those of you who've read anything about Joe know that he's a big sports fan, anything Notre Dame, baseball. He's even written a book on mathematics and sports. You may know him from his very popular contemporary abstract algebra book that's in its 10th edition, or the For All Practical Purposes mathematical literacy text. He's also well known for 40 plus years of a very successful REU program at the University of Minnesota Duluth, where he is the Morse Alumni Distinguished University Professor of Teaching. You don't get a title like that unless you really are doing something right. He's held offices and had awards with MAA, AMS. I won't list all of those. I know him because he was one of the co-directors of Project Next with the MAA for many years. So I was one of the 2001 participants, a Cardinal Dot up at the University of Wisconsin. And like many of my colleagues, we got his famous "Just Say Yes" speech to get involved, find your niche, say yes to opportunities. And that may be why I'm now a national officer in KME. But without further ado, I'd like to welcome Joe Gallian to be our keynote speaker for this biennial convention. Thank you so much for being here, Joe.
Thank you, David, for the warm introduction. I'd like to also thank the organizers. It's a lot of effort to put one of these together. And I especially enjoy conferences where there's lots of students. This is the first presentation I've ever given on Zoom, so I hope it goes well. To me, giving a presentation on Zoom is like giving somebody a hug on Zoom. It's not the best, but the intention is good. Okay, let me get started. The seeds for this talk, can people hear me? Is that all right?
Yes, we can hear you.
The seeds for this talk started in 1978, and it's been on. I always try to get a reference into the Beatles. I'm a huge Beatle fan. And it's been a long and winding road that leads to your door. In any case, here's how it got started. I was looking for research problems for students to do, REU students, some are research students. And I saw a beautiful paper in the Journal of Graph Theory. It was written by Tom Trotter and Paul Erdős. And a couple of things appealed to me. The simplicity of it, the idea was very nice. And I thought the result was nice. And what I like best about it is not what they did, although I like that, but what they left open. They left a huge amount of things open for people to follow up. And that's what I was looking for, something for the students to do. So here's the Trotter-Erdős problem. Consider a 3x5 grid with arrows. So the idea is you can travel along this grid by following these arrows. You always have to go in that same direction. When you get to the far right, then you can wrap around to the left. When you come, go vertically down. When you get to the bottom, you come back to the top. And the idea is you want to start somewhere. It doesn't matter where, it's independent. If you can do it at one vertex, you can do it at any vertex. But you start somewhere and you follow these arrows, whatever way you choose. And can you hit every point exactly once? You want to visit every point once and return to where you started. Can you do it? Okay. The first time, oh, by the way, this is Tom Trotter on the left, Paul Erdős on the right. Anyway, Tom Trotter was chairman at Arizona State for a number of years, and he was head of Bell Labs mathematical research for a number of years, and he's been at Georgia Tech for a number of years. And maybe the students don't know, but Paul Erdős is the most prolific mathematician ever. He's had the most joint papers ever. And he had a huge impact on combinatorics and number theory in the latter half of the 20th century. So anyway, another thing I like about the paper, I call that good lineage. Who has worked on this problem? Who came up with the problem? The more well-known they are, the better the problem. Although sometimes it can be too hard. But in any case, of course, they worked on the general case, not just a simple case. But you just start with an n by n grid and you pass for each vertex, start somewhere, pass for each vertex once, and to return to starting point. Okay, now, this is the way I really should draw it. This is a grid on a torus. And that way, like for example, here, see, I move counterclockwise, 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 and vertically I move counterclockwise, counterclockwise. And so there aren't any corners. When you draw it on a rectangular grid, it looks like that upper left-hand corner special or upper right-hand corner. But if it's on a torus, every vertex is really the same. So anyway, what you should do, if you're a student or just learning the subject, try some easy examples and maybe you can get some insight into the problem. So this is about the easiest non-trivial example. And my algorithm will be move horizontally whenever you can, and you only move vertically when you're forced to do so, by the rules. So I'll start in this corner, horizontal, horizontal. Now I'm forced to move vertically because if I moved horizontal a third time, I'd be back to the starting place before visiting all the vertices. So horizontal, horizontal, forced, horizontal, horizontal here, horizontal there, forced, horizontal, horizontal. Now I'm not forced, but I don't want to go here. I want to go back to the top. Okay, so that works. The reason I have these vertical diagonals, vertical vertices in blue is I'm going to call attention. What we did is we visited all the vertices on the top, and then we exit in this corner. Then we visited these vertices, exit in there, and then we visited the last row in here. So that really proves that a square, anytime you have a square, that'll work because you just cover this top row, drop down, now you cover the next row, drop down, and you'll always end up exactly where you want to end up in that lower corner. Okay, now that same proof actually gives you when one parameter divides the other, the same algorithm works. For example, take a 9×3. Well, what I'll do is I'll cover a square, cover 3 squares instead. So same idea as before, horizontal, horizontal, vertical, horizontal, horizontal, vertical. And now when I take this horizontal, I don't want to go back to the top. So I go down, but now I start all over again. And then first block you'll exit here, the second block you'll exit there, the third block you'll exit there, and then go right back to the top, which is perfect. That's what we want to do. Okay, now I want to try to convince you that a necessary condition to make this work is that the GCD of the row number and the column number, the greatest common divisor, the number of rows, number of columns, has to be greater than 1. And what I'm going to do is I'm going to take a counterexample, but this counterexample will always work, always be a counterexample when the GCD is equal to 1. So I'm taking a GCD equal to 1. I'm going to show you what goes wrong. Okay, so I'll start here, and I just want you to count the vertical moves. And remember, we have to start at the top row and end at the top row, and in fact, even in the same spot. But I just want to see how, if you start at the top row, when do you come back to the top row? So count the verticals. That's 1, that's 2. Oh, wait a minute. Count verticals. That's 2, that's 3, that's 4, that's 5. Oh, of course. If you have 5 rows and you're going, every time you make a vertical move, you move 1 row, and it's going to take 5 to get back to the top. All right. Well, then, this might be part of my circuit. By the way, these are called circuits if you can do it. Hamiltonian circuits if you can pass through every point. So this shows that if you're going to start at the top row, every time you come back to the top row, it has to be after 5 vertical moves. So the total number of vertical moves has to be a multiple of 5. You move around, you start at the top, come back, that's 5. Start at the top, come back again, that's 10. Okay, and the same thing works for horizontal moves, except this time you're starting in the left-hand column and you're going over 7 columns. And that has to be multiples of 7. So now what we have is we have the total number of vertical moves is a multiple of 5, total number of horizontal moves is a multiple of 7, and we know what the total number of moves is, that's the total number of vertices, but I have a contradiction instantly, because 7 divides 35, 7 divides 7b, so you can bring this 7b to the right. In fact, out of 7, that means 7 divides 5a, but 7 doesn't divide 5, so it has to divide a. Well, what would that mean? That would mean I have 35 vertical moves and 0 horizontal. Well, of course, 35 vertical moves, it just means you're going around the first column over and over again. Or, of course, I could have had 35 horizontal moves, but then you're just moving 35 around the top, and around the top, and never getting out of the top row. So that contradiction will always happen when the GCD is equal to 1. Okay, now what Trotter and Erdős wanted to do is they wanted to get a characterization. And what I mean by that is a numerical characterization. They don't want to look at pictures. They don't want to draw arrows. They don't want to look at grids. They just want to give 2 numbers. I give you a number like 5×7 or 4×6, And you can answer yes or no just by looking at those numbers. You don't have to draw any pictures. And when I say yes or no, that means if and only if. Every pair of integers has a definitive answer just by doing a few little calculations. And in fact, oh, I forgot to tell you the most important thing. Trotter and Erdős had the characterization, but not a good one. It was clumsy. You didn't need to draw any pictures, but you needed to do too much work. So the first thing I wanted a student to do, is a guy named Steve Curran, 1980, by the way. I said, Steve, Trotter and Erdős have a great idea, but not a good characterization. It's too cumbersome. So I said, see if you can come up with a better way to do it. And sure enough, he came up with a great way to do it. And it's incredibly easy. Plus, it's very intuitive, well, most of it anyway. And here's what it says. If you have an n by n grid, a Hamiltonian circuit means you pass through each vertex exactly once and then return. It's named after a famous mathematician. He came up with this idea of traveling around on a graph and returning to the starting point. Well, in any case, this is going to be the number of vertical moves because there's m rows. This is going to be a number of horizontal moves because of the number of columns. And of course, there's only two types of moves that has to add up to everything. But here's the crucial spot. Here's the deciding factor. If you can get this numerical combination right, you still need the GCD, the greatest common divisor of this number, the A and the B, that has to be 1. If you have that, then it's yes. And if you can't get this condition, then it's no. Okay, let's take a look at an example. Okay, so let's look at a 4 by 6. So I try to get a combination of 4 and 6, a numerical integer coefficient, positive integer coefficient, a combination equal to 24. And sure enough, there is one. And then you check the GCD. This is 3 and this is 2, and the GCD is 1. Now, actually, this tells you more. It tells you there's a circuit, but it says, wait a minute. If you draw this the circuit they're telling you about, it actually tells you exactly how many of each. There's going to be 12 and 12. All right, so when I go to draw it doesn't tell you how to draw it, but I say, well, okay, if I want to draw it, why don't I just alternate them? Because that way I'm guaranteed that there's going to be an equal number. So let's just try that. So I'm going to start here. It doesn't matter where you start. And I'll go horizontal. Now I want to alternate. So horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical. Keep going, keep going. Where are we going here? Yeah, it's coming. Okay, there it is. Oh, by the way, I call these, I think I invented this term, although it's so natural, somebody else might have come up with it. But see, I call the 3 and the 2, those two numbers, the GCD has to be equal to 1, the wrapping numbers. And what does this 3 mean? Well, the 3 means when I follow the circuit, I'm going to start at the top, I'm going to wrap around up to the top 3 times. There's the first wrap around, vertical, there's the second wrap around, there's the third wrap around. And of course, this 2 means you're going to wrap around once here, horizontally, and a second time there. So the wrapping numbers have to GCD has to equal to 1. Okay, there's Steve Curran right there. That's me. Great shirt, great hair. In any case, this is my whole REU back in 1980. That's it, just those 3 people. Anyway, some of the faculty here, older faculty, might remember the famous ring theorist from Chicago named I.N. Herstein. He had this classic book on abstract algebra, which was a huge influence on me. In any case, this Gail Letzer happened to be I.N. Herstein's last PhD student at Chicago. And she's at the NSA now. Okay, so let's try it on an 8 by 12. Now, first of all, you have to make sure that the GCD is right, okay? The combination's right, that's 96. And then again, this tells me that there's 72 vertical moves and 24 horizontal moves, but it doesn't tell me when to make the horizontal and when to make the vertical, but it gives me some information. Oh, wrong button. Okay, now I want to point out something important. That this doesn't show up in the characterization. It doesn't show up in the way that Curran wrote the characterization, but it turns out that, remember, you might not have a circuit because if you have a 3 by 5 or a 5 by 7, those two things are relatively prime. And the condition is the row number and column number of GCD has to be bigger than 1. So you might not have one. But here's what combinatorials always do when they come up with a new idea or a new object. The first question is existence. Does there exist one? And once that question is answered, the next natural question, is it unique? Well, in this case, we know this exists, but it's not unique. Once you find one circuit, there's more than one. So the Hamiltonian circuit is never unique in this case, okay? Now, remember I said earlier on what most excited me about the Trotter and English paper, they ended their paper with that theorem, not the current theorem, but the characterization, their own characterization. Of course, it's equivalent to the current theorem. But in any case, so I thought, well, what else can you do? So the first thing I thought of was, look, let's go back to the 3x5 case and 5x7 case. We know we can't hit 15 points. We know can't hit 35 points with a circuit because the GCD is wrong. So maybe what I should do is go back to the 3x5 and just delete one vertex, and try to get the rest. Try to hit 14 out of 15, because I can't hit 15. In any case, there's a great name for that. It's hypo-Hamiltonian. And hypo is a prefix that means below. For example, a hypothermic needle goes below your skin. And if I would run down and jump in Lake Superior, which is about 5 minutes away from me, and I've been in there for 60 seconds, I'd be suffering hypothermia because my body temperature would be below the normal. Okay, so that's a great name. Now, what about hypo-Hamiltonian circuits? Okay, well, Steve Curtin didn't do this, but I did it with another student. And here's what we have. First of all, I'm going to recall I always want to recall that Hamiltonian case because that was the impetus for the next case. When Hamiltonian failed, what else could you do? So remember, if you want to hit them all, the GCD had to be bigger than 1. And this is great because if you want to hit them all but 1, the GCD has to be equal to 1. It picks up the things that you couldn't do. Well, at least some of them. And by the way, and here's the condition. This is obviously necessary because that's a number of vertical moves, that's a number of horizontal moves, and the total number of moves is, well, you missed one vertex. So that's why there's a -1 there. And here's a great thing. In this case, it turns out that I want to make the contrast here. Remember, in the Hamiltonian case, if you had a circuit, it was never unique. But in the hypo-Hamiltonian case, it's always unique. It might not exist, but if it exists, there's only one possibility. And the reason why is every arc is forced. Let me try to explain what this means. Doesn't matter which vertex you omit, so I'll just omit this one just for convenience. Now, I have no choice in any spot. In any vertex, I must move a given way. And if this actually works, if I visit all 14, then that proves uniqueness. All right, here's the argument. Let's start here. Where could I go? Well, I can go here, and ordinarily I could go there, but that point's gone. So that option is totally gone. It's not there anymore. So once I move this horizontally, I claim that this vertex has no place to go but down, because if I went vertically here and horizontally here, I'd visit one vertex twice, which is against the rules. So as soon as I was forced to move this one, if I can get the mouse to work, this vertex was forced. That movement was forced this one. But now this move forces, let's see, when is it here? It forces this one. And the reason why is, look, when I come in here, I can't also come in there. I can't, because I'd hit twice. So as soon as you make that move, it forces this one. And by the way, there's an easy way to see what's happening. I'm just going down this diagonal. So this one forced, this one forced. These are all vertical force. Vertical, vertical, vertical. Now here's where the torus would come in. If I had a torus, you could see where would the next point be. It would be there, except on here I don't have a torus, but I would have wrapped around and gone to the backside. That becomes that. So that's what's now forced. And then keep the diagonal. So this is forced. Of course, this one forces this one, because if you went down here and over there, you'd have a contradiction. So again, I go down the diagonal here, and what does this mean? Well, then it's over here, and that one's forced. Now, just for fun, you look at this and say, well, of course, he visited all 14. Let's just check out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, okay. All right, perfect, it worked. Now, so a 3x5 is not Hamiltonian, but it's hypo. Let's try a 3x7. Remember, this is not Hamiltonian. Could it be hypo? Well, I'm not going to show you the arrow force. It's the same way you come down the diagonals here. And then, so look, you look at that and say, yes, it works. Just, I visited every vertex. I came in, play. There's arrows to all 20 vertices. I went in once and I went out once. So yeah, it works. But well, let's count just to be sure. So start here. Remember, I'm supposed to hit 20 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, it didn't work. Kind of 1, 2, 3, 4, 5, 6, 7, 8, 9. Didn't work. What's going on here? Well, first of all, let's prove something very important. That condition about the GCD equal to 1 is necessary, but not sufficient, because a 3 by 5, we got a hypo, but a 5 by 7, we did not. Okay. And by the way, if you suppose I remove that little circuit, the circuit of length 10, if I pulled it out, this would be the remaining 10. Oh, something good happened. That's a circuit. So what happens is in the 3 by 5 case, 3 by 7 case, I didn't have one circuit of length 20, I had two circuits of length 10, and those two circuits have no overlap. They're disjoint circuits. Like, when I pulled that first circuit out, it didn't pull anything along with it. Okay, now what? So let's recap. The 3 by 5 is not Hamiltonian, but is hypo. 3 by 7 is not Hamiltonian, it's not hypo. There's no circuit of length 21 or 20 because the GCD was wrong for 21, and we checked at the arrows, they were forced, and that didn't work either. So the question is, now what do we do? You might say, well, forget about it. But I say, well, no, let's not forget about it, because maybe something else is possible. So maybe if we can't hit one of 21 and we can't hit one of 20, maybe 19 would work. Okay. So actually, I had a new student this time, Larry Penn, next year. And I said to Larry Penn, you know what? Trotter and Erdős really asked the wrong question. The question instead of asking, if you have an M by N grid, can you hit M by N? They should have said, what's the most you can hit? I give you an M by N, and you come back with an answer. If I give you 4 by 6, you say 24. If I give you 3 by 5, you say 14. If I give you 3 by 17, well, we don't know the answer, but the point is that's what we want. We want to answer that question. So if somebody gives me a 3 and a 7, I want to say, boom, I know the answer. But we didn't know the answer, but that's the idea. That's a great question. Okay, so anyway, I said, this is the good question. And then about several days later, Larry came back and he said to me, you know what, Joe? You asked the wrong question. And I says, what's the right question? And it didn't occur to me, but this is the right question. I never thought of it. Larry says, what's the length of every circuit? So if you give Larry a 3 by 7, he'll come back with not only the longest, but the shortest, the longest, and everything in between. And for everything you give him. Okay, and here's the theorem. Oh, by the way, Penn and Whitty did this together. Okay, so say you have an M by N grid, and you say how long you want to get, any length. If I want to get Hamiltonian, I say M times N. If I want to get hypo, I put M times N minus 1. If I want to hit 19 out of 21, I put 19. Put the number there. And look how unbelievable, because in the Hamiltonian case, what did we have? We had AM plus BN equal MN. That's the number you hit. Well, now we're hitting R. And so this is the number of verticals. That's the number of horizontals. This is obviously necessary. But remember, in a Hamiltonian case, if these wrapping numbers, if those wrap GCD was equal to 1, then you can do it for the M by N. But you can do it for anything. In other words, any length that's possible, all you have to do is look at this condition. Okay. Here's some pictures again. This is Whitty. This is the Penn and Whitty theorem, I call it. Number 75 there. And that's Gail Letzer. This is a different year, but she was visiting this year. Remember, she was in the program a little bit earlier. And that's Steve Kern. I think I showed you a picture of him. Yeah. Okay. Anyway, here's me again. We're on a field trip here. There's Larry Penn. This is my whole REU. These are separate years. This is 81. That's like 82 or something like that. I didn't have photo. Those days I didn't take many photos. There were no digitals. In any case, so this is my whole REU. And I want to tell you a couple little things. This is a guy named Erwin Youngreich. He got a PhD at Harvard, and then he went straight into industry, sort of software design. And then he stayed with that company for a number of years. And then he dropped out of that company and started his own company, his own software company. And this is Larry Penn. He got a bachelor's degree at Harvard and a master's degree at University of Cambridge in England. And then he went straight to Wall Street, Lehman Brothers, Sherman Lehman, I think. Lehman, in any case, some hedge fund in Wall Street. And then he stayed there for a number of years. And then he started his own hedge fund. Okay, so I think they've done well. All right, so anyway, when a mathematician writes a research paper and you think it's publishable, you send it into a journal. The editor looks it over, takes a quick look. Oh, this looks reasonable. So that editor sends it out to a referee, maybe one, maybe more than one. And then after a number of months, a referee reports, or one or more, come back. And this might be hard to read, so I'll read it for you. The enclosed paper entitled "When the Cartesian Product of Two Directed Cycles is Hypo-Hamiltonian" is a lovely piece of work. The result is interesting, and the writing style is good. The paper is short, to the point and easy to read. Contrast this paper with the Trotter and Erdish paper. Trotter, head of research at Bell Labs, Erdish, most famous mathematician in the world. In any case, what those two students did wins hands down comparing to those pros. All right, so that's kind of nice. Oh, by the way, I should mention that I've never ever had a research or a referee's report anywhere near as good as this one for something that I did, Okay, all right, so here's the results. If you want to find every possible circuit in this 3x7 grid, just start them these linear combinations and make sure that the wrapping numbers are relatively prime to each other. So, I have a 2 and a 1, a 1 and a 0, a 4 and a 1, and so on. And remember, by the way, we forced the arrows for the 3x7, and we were trying to get a circuit of length 10. Instead, we got 2 disjoint circuits of length 20. Here's the reason why. See, the GCD was not right, but you see the GCD is 2. That's why we had 2 disjoint circuits. If the GCD is 1, you have 1 circuit, covers everything. If the GCD is 2, you have 2 circuits. Okay, so anyway, let's look at a 3. Well, this is a circuit of length 13, just to show you how they work. You have to think a little bit, but there's no forcing here. You have to think about it. And here's I'll save you the trouble here, but this is a circuit of length 19. Again, the arcs aren't forced, but you know how many they're going to be. The linear combination tells you how many vertical arrows, how many horizontal arrows. Now, someone might say, okay, this is kind of interesting, but what does it have to do with the title of the talk? The title of the talk was Symmetry Patterns. I'm glad you asked. Okay, so it turns out that there was maybe back in the 80s, that there was a guy that came to University of Duluth from Berkeley Math Department, PhD in geometry, by the way, not a common subject, PhD in geometry, and he was really interested in computer science. It was in its infancy. People didn't have PhDs in computer science in those days, but you had interest. You were probably a mathematician or engineer or something like that, but you had interest in computers. So Dunham had interest in computers, and he was a geometer, so he wanted to make computer graphics. That's the area he wanted to make a mark, and there was almost nobody doing that type of thing. And I call these Escher designs, the artist Escher. And so what Dunham wanted to do was have a computer make a design like this. Now this is actually complicated. Let me try to explain this. You don't have to know everything, but let me try to explain this. First of all, the distance from that center over to that edge, that's an infinite distance. Not in Euclidean geometry, the one you do. Euclidean geometry, if you have an x1, y1, an x2, y2, what's the distance? Difference of the x squared plus difference of the y squared square root. This geometry doesn't use that formula. It uses a different formula. And under the hyperbolic geometry, say this is the distance from this head over to that corner. So that's 1 unit. Oh, let me go here. From this middle to that little, here, let's take across those wings. Say that's 1 unit. Okay, well, look at a smaller one. That's also 1 unit. If you look at a little tiny, anywhere you look on that, that little red fish, the distance is always 1. To your eyes, it looks like it's getting smaller and smaller. But if you had hyperbolic glasses, they'd be the exact same size. So this is actually an infinite plane. This goes on forever. Okay, now what Dunham wanted to do, he wanted to give like a little triangular wedge here. Half of this fish, half of that devil, and half of that, whatever that is, a lizard or something like that. He wanted to feed that, and he'll call that a motif, and just rotate it around and rotate it again like that. And then so you feed in a little piece, and you give the computer an algorithm that says, now rotate it. Let's look at another example here. It's easier to do here. So he wants to just give a slice of this thing, and then say, for example, let's take a wedge like this. It has half an angel and half a bat, and you rotate it 120 degrees. You'll get then this angel will be complete, that devil will be complete, then you rotate another time. So after 3 rotations, you have this middle part done. Okay, so let me show you a graphic. Unfortunately, I used to have if I would have been given this talk like 6 months ago, I would have been able to show this starting point. That's called the motif, this little wedge. And I would click down here and I'd go frame by frame. I could one frame talk about it, one frame we'll talk about it, one frame talk about it. But Microsoft ditched the software that I used, Flashpoint or something like that. And now I can't do that anymore. I can't freeze frame, but I had some much cruder result from earlier, and it'll give me the idea. Let me see. See, I can stop it. I can stop it, but I can't stop it on a dime. I can crudely stop it. But notice what. Let's try if we can start that back again. Let's go back. All right. Now what I want to do is start and stop right away. Okay, that's the wedge. Start, stop. Okay, well, I've got two flips. Well, what happened is that little wedge was reflected, and it was reflected again. Now, we don't always do reflections. See that straight line there? When you see a straight line, that tells you to reflect. All right, and what we want to do is we want to complete this center. So reflect, reflect, reflect. Oh, wait a minute. Ah, dang it. Okay, the point is, once we, see, this is why I need to stop it. But once we completed that inner circle, I don't want to reflect again because I just go around in circles. But what happened was, instead of reflecting, it made a rotation. It rotated this little wedge here. And I got this. Oh, look and see. Here I got another. Okay, here I'm going to do a rotation. How do I look right here? How do I know I'm going to do a rotation? See, there's a straight line here. And you could reflect there, or you could rotate about this corner. 120, see this is in the middle, it's a threefold, so it's 120 degrees. So do I want to reflect about this or do I want to rotate? But the algorithm says, as long you want to hug the circle. You don't want, see, I don't want to go out this way. I don't want to go that way. I want to go that way. I want to hug. So watch what happens. It'll rotate. Oh, see, two rotations, in fact, two rotations. Now there's a straight edge, so it'll flip. In any case, you keep doing that. And that's the algorithm. Now, somebody might say, okay, but still, what does this have to do with those grids? Well, it turns out that notice we had two motions here, and we wanted to move around. So to my eyes and to Doug Dunham's eyes, this is the same problem. What Dunham had, he had two types of motions, a reflections and a rotation, and you did in an algorithm. You do rotate, 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 reflect, rotate, reflect. Well, it's the same as we did before, horizontal, horizontal, vertical, horizontal. And by the way, there's something called group theory, and these are symmetry groups. And he's passing through the elements of a symmetry group. And that's what we were doing earlier. And it wasn't a symmetry group, it was a group. So abstractly, this is the same problem. Okay, that's not supposed to be there. Let me give you one more quick example. Now, this time there's no reflections, there's no straight edges anywhere, but look what happens. If you count these poles, there's 6. So let's start with this white one. So rotate, each time 60 degrees, rotate, rotate, rotate. Rotate, 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 rotate. Now I want to rotate again. I finish the inner circle. So what do I do now? I see this tail here, right? I'm going to rotate that 180 degrees. So you 60, 60, 60, 60, 60, 60, 180, 60, 60, 60, 180. So these two little generators generate everything. And you might say, well, why do we want to not any miss a spot? Remember in the earlier bit, if you missed a spot here, there'd be a little hole there. There wouldn't be a lizard there. So we don't want to miss anything. Okay. Now where we are. And now here's some other patterns. I'm just going on to other patterns. Oh, yeah, this is another Dunham motif. And I used to be able to show you the picture, but it doesn't work anymore. All right, one more. This is, what am I doing here? I'm going back. Okay, there's a straight line there. So this is going to have rotations and reflections. All right, so now we're going to jump way ahead. I don't know how many years, many years. That's why I said it's a long, windy road. So it turns out back in these days, I was second vice president of the MAA. MAA is Mathematical Association of America. And you're on an executive committee, and they send letters around what's happening, coming up, and we need somebody. Does anybody know somebody that does this? Somebody can do that, that type of thing. And I got a letter from the executive committee saying, look, every year the National Science Foundation has a day at the National Science Foundation Day of Congress or something like this. So anyway, what they do is every year they organize it. Well, the NSF doesn't do it, but they ask the societies, American Chemical Society, American Biological Society, and so on. They write letters to the society and says, look, we'd like to have you ask one of your members who would be willing to come to Washington, D.C., put on a poster session and be able to talk to Congress people and their office aides or assistants and so on, and say what you did with your NSF grant. Well, that's what we'd like. And so the letter that came out to the MAA Executive Committee said, do we know anybody who'd be willing to do that? Go to Washington, D.C. They had an NSF grant and talk about what they did, or have a poster session. I shouldn't say talk, but you talk when people come up to look at the poster. So anyway, and the letter had something that caught my eye. It said, first of all, you should bring students, one or more students. And second of all, it should have pretty pictures. Oh, pretty pictures. I got great pictures. So I said, I'll do it. So they said, okay, you're my man. Okay, so here it is. There's me. I had 2 students, Sarah Moss, Melanie Wood. Here's the exhibit, the Rayburn building. This is the House of Representatives, the one that was stormed. What was it, January 6th? Yeah, right there. Too bad I wasn't there then. Well, maybe it's a good thing I wasn't there then. In any case, so anyway, this is what it is. And notice it starts at 5:30 in the evening because the staffers they'll drop by on their way home. Okay, so earlier in the day, Tina Straley, she's the executive director of the MA. She says, what we normally do is we like to stop into a few, since I'm from Minnesota, let's stop into 1 or 2, Congress people, senators, congressmen, or whatever, and just chit chat for a few minutes and tell them we're thankful, thank you very much for supporting mathematics, for supporting science. Okay, so I did that, and by the way, this is Melanie Wood. She's now a full professor at Harvard. And this is Sarah Moss. She's a full professor in philosophy, not math, bachelor's degree in math, and philosophy, at Michigan, University of Michigan. And that's the senator. And by the way, he died. He was a hero of mine, political hero of mine, but he died in an airplane crash just a few years later. All right, anyway, so there's my exhibit. There it is. And what I did was, I think it was this one. Yeah, this one. I had something like 50 or maybe 100 full colored photographs, not on my home machine. And many years ago, I went to the printing office. I said, print off me high gloss photos, 50 photocopies. Yeah, I'm gonna take them with me. So anyway, we had a table. We had a table at the, at the poster session, and table in the sense that we stood there, and I had my 50 little handouts there. And okay, so right off the bat, as soon as the thing started at 5:30, 2 young people came over, and they were smiling and looking, and they were about in their 30s, and they said, "Oh, these are great! I love these!" And Sarah and Melanie were telling them some of the math about hyperbolic geometry and infant plane and all that. And I'm saying to myself, hey, this is exactly what the NSF was hoping for. Some staffers or whatever to, hey, come back on Monday and say, you guys missed a great exhibit over there. There's math posters were fabulous. So, I said, take some of these home and put them on your refrigerator. Any case, so I said to them, who do you work for? Do you work for a senator? Do you work for a congressman? Who do you work for? And they sort of chuckled and they says, oh, we don't work for any politicians. We're the caterers. They're the one that the crackers and the wine and the cheese. So I made a huge impression on the caterers. All right. In any case, this is about 6 months later, and this is Math Awareness Month. They don't have that anymore, but for many decades, they had every April was Math Awareness Month, and every year there's a different theme. I should have looked them up. I don't remember a handful, but one was like math in the oceans. One was math and the weather. One was math and manufacturing. One was math and symmetry. One was math and medicine. Okay, so anyway, I got a letter from the executive committee, Ann Watkins and Tina Straley, and it was the same type of letter. And he said, every year, a few of us, the president of the MA, not me, president of the MA, Ann Watkins and the executive director, those 2 people meet with counterparts from the American Mathematical Society and 2 more people from the applied mathematicians called SIAM, it's applied mathematician. And those 6 people say, okay, well, what are we gonna do for 2003 Math Awareness Month? And when you go to these meetings, each group is supposed to come forth with an idea, okay? But it's not just an idea. You have to say, okay, well, here it is. Well, I guess it's more than an idea, but you're supposed to come to me with an idea. So here's what I did. I talked to Doug Dunham, and I told Ann and Tina Straley, the people that are going to be at the meeting, I says, I have an idea for math and art. That's what I'd like to do. And then here's what I told them to do. When you go to the meeting, I don't want you to walk in and say, the MA's ideas will be math and art. and just wait to see what they say. I said, I want you to go in there. We already had the poster made up. Here's the poster, and I had it framed and shipped to Washington, D.C., because that's where the meeting was. Okay, I want them to walk in with a beautifully framed poster. And I created a website, Math Awareness Month 2003 website. And on that website, I had 12 names of famous people that connect math and art. And each of those 12 agreed that if this is approved, they agreed to write essays about math and art. Each of them has a math and architecture, math and whatever. What do they call it? Math and I forget what they call it when you knit, math and knitting. In any case, so they all agreed to do this. And so that's all set up, but nothing's been approved yet. But see, the point is, you have to sell. You just walk in our idea. Our idea is math and art. You have to make a big, bold presentation, blow them away. Okay, anyway, well, it turns out that they weren't super impressed, but nobody else had any ideas. They said, okay, we'll go with that. So there it is. By the way, I had the NSA, I asked the NSA if they would pay for, I think we printed like 7,000 of these things in full color. These were like 17 by 20 inches. We mailed them out. Anybody that would write the MA, we would send it to you in a tube. So the NSA paid for all that. Okay. So anyway, how do we fix their time here? I got lost. I think we're all right. Okay, so what are other ways to create symmetry patterns? Okay, well, it turns out, this is in 2005 now, it's a long and winding road. So in 2005, at the beginning of, we have a graduate program at UMD, master's degree program, and I volunteered to give a talk that the graduate students just shows up. Maybe it was even before the classes started, but it was either right before classes started or the first week or something like that. And somebody said, well, can you give a talk to the new graduate students? Just a talk on some stuff that they might like. I said, sure, I'll do it. So anyway, I gave this talk, the talk you just heard. And at this point, by this point, the talk, this would be sort of the end of the talk that Josh Jacobs heard right here. But in any case, so Josh Jacobs come up afterwards, and it turns out he was older, he was about 30. And he got a bachelor's degree about 8 years before, and he had spent the first 8 years in computing, software development or whatever. Everything had to do with computing. So anyway, he comes up afterward and he said to me, I love to do something this. I want to do something just like this. And I said, okay, that sounds great. But let's think about it. I had to think about something. In any case, I eventually came up with I found something of it. This is not my idea, but I found it. Okay, famous number theorist called Lenstra. Anyway, it's a little complicated, but let me try to give you the gist of it. What you want to do here, you want to make a symmetry pattern from a fixed pattern. We're not going to do motifs and generate like we did. We'll take a finished pattern and a pattern we like, and we want to modify it. We want to create a new pattern from the original pattern. So what we're going to do is we're going to scan in the original pattern, whatever that original pattern happens to be. We'll scan it in the computer, and the computer will pixelize everything, have coordinates. But then we want to go mod the integers. Like if I say 4.2 mod the integers, it means every integer is 0. So when I say 4.2, that coordinate would just be 0.2. If I say 5.7, that coordinate would just be 0.7. That's what mod out the integers mean. You just take the decimal part. Okay, then you get equivalence classes. See these two parallel lines, they're 1 unit apart. And these parallel lines are 1 unit apart. Now here's what happens. If you do this, if you take the image and you do that modding, and then you use this function, that's the Euler constant, that, what is it, 2.71 something or other, to transcend the number, in any case, and you apply this function to all the pixels, just use this exponential function, and the z is what you're transforming, and then these parallel lines become concentric circles. See, parallel lines become concentric circles. And here you're modding out by E again. It's really E comma E. Okay, and down, oh, I goofed up there. Okay, down here, this is a different mod. Here I'm going to have a complex. This is a complex transformation. You can think of this as the real plane to the complex plane. If I use the complex plane, then I have this funny number, W here. And this W, notice I have pi involved, I have a log involved and dividing by 2 pi. And then you're going to mod out that star means, by the way, the star means that you exclude 0. This is a multiplicative group. You include 0 because we're going to multiply these numbers. In any case, so here you're modding out by, it's the complex numbers throwing away 0 and it's the real numbers. Okay, so here, these lines, instead of concentric circles, become spiraling. See these red arrows or red dots? You're spiraling. Okay, so let's look. This is going to be my motif. That's Escher. And this is when you apply the real transformation. So I get See the concentric, these little 4 fish, a concentric circle in there. There's a big circle and a circle there, and circle, 4 fish within 4 fish within 4 fish. And here's a spiraling one, same pattern. They're spiraling in towards the center. Here's a devil and angel, an Escher print. For some reason, I don't have the real transformation, but there's spiraling angels and devils. Okay, and then Josh Jacobs, let me see the time. Okay, I'm about on time. Josh Jacobs said to me, you get the best results for these things he did if you have a circle in the middle. Then he shows me an example. That's Josh Jacobs. So that's the spiraling. That's a complex transformation. That's Josh Jacobs within Josh Jacobs within Josh Jacobs ad infinitum. Okay, and I said, fabulous. I was just completely blown away. And really, he showed me this before I saw all those patterns. That was just the first thing he showed me. Okay, and then I said to him, well, look, if it works best with a circle in the middle, why don't you use the most famous image ever with a circle in the middle? And he says, what's that? And I said, there it is, Sergeant Pepper's Lonely Hearts Club Band. I says, apply your transformation to that. So there's the real transformation, Sergeant Pepper within Sergeant Pepper within Sergeant Pepper. And that's the spiraling transformation. And I have one more transformation here. Let's see, I think, is this it? Yeah, okay. Let's see, I hope this works. All right. Whoa. It was 20 years ago today. Sergeant Pepper passed the band way. They've been going in and out of style. But the girl needs a razor smile. Say, introduce me to the actress who always is. Sergeant Pepper, Lonely Hearts Club Band. That's it, thanks. Is anybody still there?
That was fun. We're having so much fun.
I didn't hear what you said.
He might be having some audio issues.
Oh, could you hear it? Could you hear the audio during the video or not?
Yes, we could hear that.
Okay. How about my singing?
That was great. That was great.
Thanks. By the way, my hearing's not great, so I might have to ask you to repeat something. But it sounds like I think I can hear you fine.
All right. If we are ready for questions, we've got a few already in the Q&A section. The first one from Marcus. When you decided to work on contemporary abstract algebra, was it out of passion, necessity, or both?
What was it? What was the first one?
When you decided to work on contemporary abstract algebra, was it out of passion, necessity, or both?
I was definitely out of passion. But what happened was I didn't intend to write a book. But what happened is I had a book and it was a good one, but I thought it had some shortcomings. So for every chapter, I'd make up my own examples, and I'd make up a few examples of my own, which I thought were better or whatever, different. And then I'd always make up a few little exercises. In fact, I'd make up a fair number of exercises because I would give them on the exam. I'd say, oh, I'm going to make up some exercises for the exam. And so I kept doing it each year. And then sometimes, maybe a proof was not as, I thought they were shorter. I like to try to get shorter proofs. I spend a lot of time on trying to find simpler proofs. A lot of times there's certain proof and people keep using the same proof because that's what other people use. I try to find simpler proofs. And every time I succeeded, I would save that. And over a course of many years, I kept accumulating more examples of different proofs, a new topic. Here's a little topic that wasn't in there. I'll throw a little bit of that in there. In any case, after about 10 years or whatever, I said to myself, gee, I have a pretty good stack of new stuff here. And so I thought, maybe I should make a book out of it. And in fact, I made a partial book out of it, whatever. And I just a manuscript, and I sent it in to a publisher, and I said, here's an idea. I didn't want to do the whole thing, but here's a good start. And what do you think? and they were very enthusiastic about it. So that's what it did.
Awesome.
Oh, wait, other thing. See, the book I had didn't have any historical notes, so I would throw in the historical notes. They didn't have any inspirational quotes, so I'd throw in that. Jokes. I kept every time I thought the book I was using didn't have some stuff that I thought would be nice, I just kept adding it. Photographs, postage stamps, things like that.
All right. The next question from Brian Dawson. Did you ever try the transformations on the music also?
No, that's perfection. I can't beat the Beatles. No, I didn't. First of all, Josh Jacobs is the one that did these transformations, not me. And he was interested in the pictures, the graphics of it. Same with Dunham. But I never tried to. My guess is that it wouldn't sound good, but I don't know. See, I love harmony and melody and harmony. That's what I love. And so transforming it might not sound so great.
All right.
Go ahead.
Next question. Is there any way I can get more information on the subject, a paper or something, or would you recommend the book? That's from an anonymous attendee.
You mean the stuff I talked about in this talk?
Yes, I believe that.
Yeah. Why don't you send me an email note and I'll send you some references. First of all, there's some of it. There's a fair amount of it in my book. There's a chapter called KME graphs. There's some of it in my book, a fair amount of it. But then I can send you some more references. There's a huge amount of stuff that's been done. A lot of it's done by my own students, besides what I talked about. For example, if you remember when we had a whatever it was, a 3x5. No, let's take a 3x7. So we couldn't hit 35 points. We couldn't hit 34 points. But you could ask the other question. Go back to 35 points. Instead of deleting a vertex or two vertex, let's allow you to duplicate one vertex. So now you'll pass through 36 points altogether, one twice. And by the way, we solved that problem. That problem is completely solved. And again, if it exists, it's unique. There's a uniqueness argument. It's the same argument. Remember, we had AM plus BN equal to M minus M times M minus 1 when you throw one away. Well, when you add one, it'll be plus 1. So the same argument that worked for the GCD thing, for the minus 1 works for plus 1. Same argument. In any case, now if you go back to a 3x5, say you have a 3x5, remember you couldn't hit 15. But if I allow you to duplicate one, you can hit 16. And by the way, the GCD, the wrapping numbers would be 2. The GCD, the wrappers number would be 2. And here's what happens. When you add a point, the necessary and sufficient condition is the GCD, the wrapping numbers equals 1 or 2. See, the fact that if you want to hit it exactly the right number, the Hamiltonian case, the GC had to be 1. But if I add an extra point, that allows you more freedom on the GCD. So a 16 definitely has that's called what's that called? Hyper Hamiltonian. Hyper means over the top. So that's called a hyper Hamiltonian circuit. I'm going on too long, but other things we did was, say you have a 4x6, or let's take a 4x6. Inside of a 4x6, I can take divisors. I can take a 2x3 block out. Instead of removing one point, let's remove a whole block. It's like you're moving the middle of the picture. Now can you circle around with that thing in the middle? So what we did, that's called, the big group's called a group. And the original, the M by N is a group, but then you remove a subgroup and see if you can, well, we can do that. When I say we, I mean me and my students and so on. One of my students turned out to run an RU program, and he gave some of these problems that I talked about today. He gave them to his students, his RU students. So second generation.
Very cool. You may have touched on this just a little bit, but another question from Marcus. Was the idea to put quotes in each chapter your own, or had you seen other authors employ this practice?
I seen the main one I saw was, where I really got the idea was Don Knuth. He has this incredibly classic book called The Art of Computer Programming. It's an unbelievably important book in the history of computer science. And anyway, he had a quote in there. in graph theory, a very important graph is a tree in a graph theory. So he had a quote, so he had a chapter on trees, and he says, "No one I think is in my tree, you know, I must be higher." Oh, that's Strawberry Fields for her. And I said, what a great idea. Although I sort of took it to extreme, but other people have done it before me. I think I just overdid it. I tend to go overboard on everything.
Another question from Anne. Did you do research as an undergraduate student yourself?
No, it was unheard of when I went to a state teachers college. Undergraduate research was, I could took a whole talk just on undergraduate research, but even back in the 60s and 70s, the general feeling was that in mathematics, you could have undergraduates do research in biology and lab sciences because they could do, you know, measure things, fill things, you know, keep measurement, you know, keep records or whatever. But the general feeling in the math community was, they had a whole conference at Carleton College about this in the 19s. I have a whole article about this, about the history of research in the United States and undergraduate students. Anyway, the feeling was that undergraduates they just weren't capable of it. It wasn't a good idea. You'd be better off taking extra courses or something like that. It was discouraged. And there's always a few geniuses around, of course, that, you know, Noel Melke's got a full professorship at Harvard when he was 20. So anyway, full professorship in you know, but generally thinking, it was not considered to be a good idea, and that persisted up even to like the 80s and the 90s, and that's pretty much set aside now. But there was a lot of pushback against involving undergrads in research for decades.
Interesting. A question from Joshua. Do the circuit traversals relate to the free groups on 2 letters? Can this be generalized to produce or to a product of more than 2 groups?
Well, some of those Dunham pictures actually, you mean 2 generated groups, 2 generators? Any case, oh, I see, more than 2 groups. Well, I'm confused now. Anyway, if you're talking about a generator, it can be done, but I don't think it's very interesting. But I never looked in it. But if you try free groups, let's see, the fact that they're free means I'd have to think of it. I think it'd be boring. But I never considered the question. It just so I'm just taking a wild guess. I think it would be either intractable or it would be trivial or possibly hard, I'm guessing.
All right. One last question from Marcus. Do you think there might be any nice relationship between wrapping numbers and the orbits of elements under group actions?
I'm guessing no, but that's a total guess. I never thought of it because one is a question about a graph, and another question. They're kind of completely different. They're completely different things. The action's completely different, and the goal is different. So I don't think there'd be a connection, but I could be surprised. It never occurred to me to think about that. But I don't know if let me rephrase that whole problem, by the way. You, instead of phrasing it the way I did, you could just say, suppose you have now you're going to see, look, all you're doing is this. Suppose you had a 2-generated group, a finite group, say a 2-generated group with 20 elements, call the elements A and B. And then suppose you ask the following question. I want to start with a product. I want to multiply A and then multiply by B. You get to choose. But at each stage, I don't want to hit the identity. At each stage, when I multiply, I don't want to get anything I've already hit. So, you know, you have A times B times A. And you always either put an A or a B, but you never want to wrap back and hit an earlier element. And you want to keep going until you've hit every last element. So when you made that last multiplication by either A or B, and then one more point, and then if you either follow that by an A or B, you're back to the beginning. Okay, that's the same problem stated in mathematical terms without drawing any pictures whatsoever. It's exactly the same, except with the way I did it, you could picture what's happening. And when you can picture, you can get a lot better ideas. You can see what the pattern is.
All right. Well, that concludes the questions that we have. So
Oh, wait a minute. Let me say one thing.
Yeah.
This is almost a record for the most number of questions I've ever had. Of course, you took the freedom to allow me to go way on and on and on and on. But I really enjoyed the questions, and I really enjoyed the opportunity. So thank you very much.